We've been looking at radioactivity, this idea that nuclei just decay for some reason and they're not stable. And we want to take that a step further now, right? And basically, we've discussed the fact that there are only so many elements, okay, and they're in the periodic table. There's about 100 of them, okay, and sorry, you find it in the periodic table in this, okay, so on page 79, okay, also in your, if you have them, I'm not sure if you have them in your school diary, okay, but the periodic table is here, and remember, atomic number of protons, and that's the list. Basically, if you were doing a periodic table for physics, just be a list from 1 to 100. Okay, number 1 will be hydrogen, number 2 will be helium, and so on. Okay, as it is. Okay, here. Okay, so you have the starting at 1, 2, 3, 4, and it keeps going up like that. Okay. Now, as it turns out, we're interested now in the nucleus, not in the atom. We're interested in the nucleus, nuclear physics. Okay, and in the atom, when you were in chemistry last year, you were talking about the noble gases being the most stable in row 8, and they had a full outer layer of electrons. This is irrelevant to the nucleus. Okay, the nucleus is completely different, and as it turns out, the nucleus, the most stable nucleus, is the iron nucleus. Okay, and the iron nucleus is right here, 28. Okay, if you can see it. Okay, you probably can't. Okay, 28. Right. Okay. Sorry, 26, let's get it right, 26, atomic number 26, 26 protons and a certain number of neutrons. That's the most stable. If a nucleus is bigger than that, it wants, as such, it wants to be more like iron. Iron is the magic nucleus. So in the periodic table in the physics lab, iron is circled. Okay, if you have a periodic table in one of these or anywhere else, circle iron for physics. Okay, iron is the most stable. That's the one we want. Right, now, basically, you have two possibilities. The nucleus can be much too big or it can be much too small. If it's much too big, well, what do you think might happen to it? Well, it makes sense. You want to make it smaller, it can split in two. Okay, it can split in two. And this is known as fission. This is known as fission. So if you have a very big nucleus, it might split in two to make into a smaller nucleus. Okay, so what it is fission is the splitting of a large nucleus into two smaller, similar sized nuclei. And the important thing is with the emission of energy and neutrons. Okay, the emission of energy and neutrons. Now, we'll write that up here. Okay, so fission is splitting of a large nucleus into two smaller, obviously, similar size, and that's important. So it's not just a chip in the emission of energy, and that's the important thing, because this is the fission bomb, this is nuclear bomb, this is Hiroshima and Nagasaki, this is nuclear reactors. When this happens, energy is released and neutrons. Now you may wonder, how is energy released? Well, what comes after is more stable than what came before. And we need energy, if you remember, we need energy to hold the thing together before. So if we need less energy to hold the nuclei together, there's energy left over and that's released. And that's the bomb, okay, or whatever that might happen. So this is fission, right? So we'll next week in our life classes we're going to look at some of the nuclear equations, but you could have uranium would split into krypton and radium and so on. Now the question is, how does it split? What happens is, you look at it general, and you'll have some video clips to look at now as well. Very large nucleus, like there could be 300 protons and neutrons in total there. And what happens is a neutron is sent in. Now a neutron is a magic bullet because a neutron is neutral. So even though all this is plus charge, it would repel a proton, but a neutron is neutral, so it can sneak in. Okay, so undercover, right? So the neutron comes in, and what happens is the neutron comes in, and effectively, it's a bit like Jenga. Okay, if you ever played the game Jenga, the nucleus was unstable as it was. You've added another neutron, it becomes more unstable, and what actually happens is it becomes very unstable, and it splits into two parts, two smaller, similar sized parts, and a few neutrons. Okay, a few neutrons as well. Okay, that's what happens, right? Now, what can happen then is these neutrons can cause another fission. And what I'm going to talk to you now about is something that up to this year people kind of have found very hard to get, but I think now you're going to have no problem, because we effectively have an R number, right? So when you're in the vaccinations, the R number, or sorry, in COVID, the R number talks about how many people are infected by an infected person. And if we keep the R number under 1, we're in business, because eventually the whole thing will fizzle out. If it's much more than 1, we have the problem we have at the moment. Okay, so that's what an R number is. Effective is an R number in fission as well. If on average one of these causes another fission, the reaction keeps going and it's nice and steady and stable, and it's releasing nuclear energy and you're in control. If it's less than 1, it fizzles out, and that's the word we use, it fizzles. Okay, if it's less than 1, it fizzles out, the reaction stops, no good to us. Okay, if it's more than 1, we have a problem. It just gets bigger and bigger and bigger and bigger, a bit like COVID at the moment. Okay, and that's an explosion, boom, right? Okay, so for nuclear energy, you want the R number to be 1. You want, on average, one neutron of the 2 or 3 that you get in each fission causing another one. Okay, so it's quite interesting. Okay, so let's go back to it. Okay, let's look at it. You have a large nucleus that's unstable. It wants to be like iron. Iron is the golden boy or the golden girl. Okay, it wants to be like iron. So you split it into 2 nuclei. Okay, 2 smaller nuclei. Okay, of similar size, more neutrons, plus energy. Okay, plus energy, and there you go. Okay, so that's, I want you to have a feel for that now before we go into live class next week, because we'll be really building up on all this in the live class next week. Now that's fission. Now the second question is, what happens if the nucleus is really small? Okay, well, you see, effectively what happens is they join together. Extend, wouldn't it? Okay, and that's called nuclear fusion. Okay, so if you fuse things together, they join together. You remember in junior cert science, you spoke about fused joints in your skull, so they were stuck together. Okay, so fusion, well, let's have a look at it. The joining of 2 smaller nuclei to make a larger nucleus. With the release of energy. Now, okay, I want you to take note of that. Right, this one is slightly, it is different in that if you have 2 small nuclei, okay, and you want to join them together, the problem is these are plus charged, these are plus charged. They want to repel. Okay, so it takes a huge amount of energy to get them together. And then you get a huge amount of energy. Okay, so it's kind of bizarre. It takes a huge energy to get them together, but once you get them together, they join together, okay, to form a larger nucleus, okay, which is more stable, so there's a release of energy. So the problem with fusion is it takes a huge amount of energy to get it going, but once it gets going, it keeps going. You all know a fusion reactor. You all see a fusion reactor or feel the effects of a fusion reactor every day, because the sun and every star is a fusion reactor. That's where the energy from the sun comes from. Okay, small nuclei in the sun joining together to create bigger nuclei, release of energy. So the sun is a nuclear reactor and it's a fusion reactor. At the moment, we can't economically make energy using fusion reactors. Okay, if we could, we'd solve all the energy problems. So if you want to get past Elon Musk, and if you want to get past whoever else, Jeff Bezos, okay, if you want to get to be #1 richest person in the world, come up with cold fusion. So getting fusion to happen without having to put in loads of energy, and then you'll be the richest person in the world. Okay, so that's fusion. So we have fission and we have fusion. So effectively now we have 3 things. We have fission, we have fusion, and we have radioactivity. So we'll just recap on radioactivity because I want the 3 of these together. Okay, sorted. Okay. So remember what radioactivity was from yesterday's lesson. Okay, radioactivity. Now radioactivity is different. Let's think about fusion and fission. Fusion, you had to send neutrons into it. So it wasn't spontaneous, it didn't just happen. Fusion, you have to give huge energy to get them to come together. not spontaneous. Radioactivity, spontaneous. It means it just happens, just like that. Okay, right? It's like deciding to have a cup of tea this morning, and you get you fill your cup with water and you put it on the table and you wait for it to boil. You'll be waiting, okay? Because heating water to 100 degrees Celsius is not a spontaneous process. It requires energy. Radioactivity is spontaneous, okay? So the spontaneous disintegration of an unstable nucleus. Now, if it's spontaneously disintegrating, it's pretty obviously unstable, but that's okay. We like adding what's obvious. It's called a tautology, okay? With release of alpha. And we have our three types of radiation: beta or gamma radiation. So they are the three ways that nuclei can change: radioactivity, fission and fusion. In each case, energy is released, okay? In each case, energy is released. Over the last few days, we've looked at the nuclear equations, and on Tuesday and Wednesday and Friday live, we'll be practicing all of that and getting our head around it. But I want, like, the really important thing is you have an understanding of fission, fusion and radioactivity. We have our formula. Okay, remember, we have our idea that the neutron is 0, 1, the proton is 1, 1, the electron is minus 1, 0, and the alpha particle is 2, 4. Okay, that's the proton. We write it as P, whichever we want to write it. We'll come back to those on Tuesday. But I expect you on Tuesday to have gone through all of these, have a good kind of understanding where we're coming from, and then we're really hitting the road running next week, and we're doing a lot of work on paper and so on, and we're going to, that's next week's work. And then the following week we go back to kind of introducing a section and then going on like that. So it's kind of week on, week recording, week alive, week recording, week alive, repeat a plan. Okay, so I've extra clips from YouTube for you to watch here as well, to kind of give you a feel for radioactivity, fission and fusion. So have a good look at these over the weekend, today and over the weekend, and we'll see you on Tuesday. Remember, live class on Tuesday, so make sure you have that you're available for the live class on Tuesday. Okay, thanks a minute, bye bye.